Alright, so I'm gonna finish this video, hopefully, and then I'll look on Paul's online math notes and I'll check and see what I can do, I guess.
It's about limits that we're gonna discuss. Were there any questions on that, by the way? As my back is turned to you so I can't see you, raise your hand. Any questions? Seriously. All right then. A couple properties. Let's say that we got two functions, f and g, and both are continuous at a certain point. If f and g are continuous at a certain point, then all of the following statements are true. Firstly, if f and g are both continuous, f plus g must also be continuous. F minus g must also be continuous. F times g is continuous. At that point. At that specific point. So if f's continuous and g is continuous at a certain point, then we can do f plus g, f minus g, and f times g, and they're all continuous at that exact same point. Does that make sense to you? Where it wouldn't be the case is, let's say that f was continuous, but g wasn't continuous at a certain point. If you add them, well, then g's still not continuous there, right, no matter what you do. So that wouldn't work. The other one is, well, you probably figured out, but f over g. Now, I'll say this. F over g is continuous at c. Unless what happens?
G equals
Sure.
0.
G of c, actually. G of c. Because we're talking about at the point c, right? If g of c equals 0. If c, when you take the limit of g and as you're approaching c, if that goes to 0, well then you're divided by 0 and you can't have that. So it is continuous at c unless g of c equals 0. And then you'd have a problem. If it does, because we're going to see this in just a moment, if g of c does equal 0, what does that tell you about your function? Firstly, is it continuous? Secondly, there are two, oh now I hope you remember this. There were two cases when you divided by 0. There's two cases of what you could have. Name one. A whole
Or
asymptote. So, if g of c does equal 0, there is a discontinuity at c. There's discontinuity at c. Of course, we're speaking just of this, though, okay? F would be continuous and g would be continuous, but f over g, there would be discontinuity at c for f over g, for that division of those two functions. Are you guys okay with that? That all these are okay except for this one? And if this is the case, if g of c does equal 0, then we have a discontinuity, and that's either a whole or an asymptote. You remember that? I'm going to actually define that for you later and give you the notes on that. We've just kind of spoken about it. I wanted to preview it so that way when you got here, it was like, oh yeah, that's easy. We've already talked about that. So it's going to be very easy in just a moment. You're like, yes, I get this because we already talked about it. But before I do that, I do have to talk about one more thing. It's going to be kind of interesting to you. Scott?
So just to recap,
It wasn't on this, right?
no.
Oh, good, because this is
Just
getting nice.
if it's 0 over 0,
Uh-huh.
and it's an asymptote.
No,
It's a
no,
whole.
we're going to talk about that right now.
Okay.
Well, not right now.
Later.
We're going to talk about that in
At the time.
3.5 minutes. Roughly. Not roughly. Exactly. Okay. Do you remember that if a function is continuous at any point C, I hope you remember because we just talked about it. If a function is continuous at C, here's what we know. The limit of the function as x approaches C equals not C, f of C, yes. Does that look familiar to you? That was the definition of continuity right there. It said this exists, and they equal each other. Remember that? That was number 3. So this is our definition of continuity. If we're continuous at any point C, then that has to take place. But I want to refresh your memory on something. Do you remember what could happen for a polynomial? When we first introduced limits, I did this. I gave you the properties, I worked through a specific polynomial, and I said, hey, can we do this for every polynomial? You're like, yeah, this is awesome. Like, yeah, I know, right? And you're like, yeah, that's cool. Do you remember? You remember? Let me even make it easier. Make it a C for any point. Do you remember what you can do to find the limit of a polynomial? Does it involve a lot of work?
Just plug it in.
You just plug it in, which means in this case, if I'm trying to find the limit of a polynomial, so P of x is a polynomial, you just plug it in. So what would the limit of a polynomial be as x approaches C? What would it be? P of C. Very good. Oops. This is interesting. I've just proved something for you in kind of a simple way. It's kind of nice. Do you see that this looks a whole lot like that? This was the definition of continuity, right? This we know we can do for any polynomial, true? What this says is that every polynomial is continuous everywhere. This is always the case. So we just proved that every polynomial is always continuous. Isn't that interesting? Every polynomial. That means everything like 3x squared minus 2x plus 4. Guarantee it's continuous. It's a polynomial. As long as it doesn't have square roots, because that's not a polynomial. Negative exponents, because that's not a polynomial. Fractional exponents, because those are roots, right? It's not a polynomial. As long as it just has those positive exponents to it and there's no fractions, it's continuous. That's what a polynomial is. This says that every polynomial is continuous. That's kind of cool. So what this says is any polynomial is continuous anywhere. That's very cool. Big statement. Every polynomial is continuous everywhere. If we combine this idea with this idea, check it out. Combine this idea, every polynomial is continuous, with this idea of this is always going to be continuous provided that g is not 0. What that means is that every rational function will be continuous everywhere except where the denominator is equal to 0. Because a rational function is a polynomial over polynomial. Do you buy into that? So it says polynomials are always continuous. Rational functions are always continuous unless the denominator equals 0. That's what these two statements say together. So a rational function which is like p of x over q of x, where these are both polynomials, is continuous everywhere except continuous everywhere, except where the denominator could be equal to 0. In other words, where this happens. At that point, you're going to have a discontinuity. That's what we said, right? If the denominator is equal to 0, you will have a discontinuity at that point. What I've already told you is that that point will either be a whole or an asymptote. Remember that? That's the two things we could have. So we're starting to put everything together. Polynomials, always continuous. We just proved it with our limit. Rational functions, always continuous, except where this happens, because we know that we can take, look at that, two continuous functions. If it's rational, that means they're both continuous because it's a polynomial of a polynomial. That satisfies that. They're both continuous everywhere. If you take it, this will also be continuous unless the denominator is 0. And that's all I'm saying here, is except where the denominator equals 0, at that point, you will have a discontinuity, either a whole or an asymptote. That's typically, this is 95% of the time, what happens with wholes and asymptotes. Now, we've seen a case where this didn't work. Okay, we already saw that where we had 0 over 0. If you have 0 over 0, you can typically factor. Well, you will always be able to factor. Typically, unless you're dealing with like a trig function. But if you are dealing with rational, okay, let's just stick with rational for right now. If you have this and it's rational, you will be able to factor it. You will be able to cross something out. That will happen here if it's a rational function. I'm not saying square roots. I'm not saying weird exponents. I'm saying polynomial over polynomial. You understand the difference there? That will happen. Now, does it always take care of every problem? No, we already saw that it didn't, but it's a good place to start. If you have this and you cross it out, that's typically a hole. All right, that's typically what happens. If you cross it out and you still have this, where you have a number over 0, that says you can't cross it out. You're going to have an asymptote there. That's typically what happens here. Some expression over 0. You with me on that one?
No, you said C over
Constant.
0. That would be the constant.
Some constant.
Oh, just any number. Okay.
Some constant. Because when you evaluate the limit, right, you plug in a number for it.
Yeah.
If you have a number over 0, it's probably an asymptote. Then 95%, okay? Every time, I don't know. 95%, that's what happens. Would you like to try a couple examples?
Yeah, sure.
Of course you. Math class. Have you understood everything we talked about so far?
I think so. Examples help.
Well, yeah.
Well, examples tell us whether we're really lost or not.
True. I'm thinking probably not. What we're going to do with this problem is I want to find any discontinuities.
I think I did this. In the also on the math notes problem.
Tell me what you know.
Alright, so I'll set this equal to 0 first. Okay. Divide the x out maybe? Or no, I can't do that. I'd have to divide by -6 by x. That's factors. I knew 2 would be, has to be 1. -2. Yeah, okay. Okay. So I probably want to plug these in, right? Just in the numerator, because I already know it's gonna happen in the denominator. Then -3 squared minus 4. 0, 5. So whole at x equals 2, asymptote at x equals -3. And it didn't ask for anything else, like the limit or anything, so.
About discontinuities with a rational function like this one. Tell me what you know about discontinuities. Where do they occur?
0.
When the what equals 0, the numerator or denominator?
Denominator.
Denominator equals 0. So, how are we going to find discontinuities for rational functions?
Set equal to 0.
Sure. Set equals 0, that's going to involve some factoring, absolutely. Essentially, all you're doing is finding domain. Remember finding domain? Well, we had problems with domain. We already really covered this. When you cover domain, you basically cover where your function is not continuous. We're just doing it for real now, talking about continuity. So you've already basically done that. If you set your denominator not equal to 0 and solve it down, you're going to find out those points that you cannot have. So however you choose to do that, you need to find your discontinuity. So if we set our denominator equal to 0, what that's going to tell you is where you are not continuous at. The points at which you are not continuous. How about that? It's better English. Better English. Can you factor that? Jeez, I sure hope so. I really do. Did you get 2 and -3 as well? Now, I want you to go one step further. I want you to identify whether those things are wholes or whether those things are asymptotes. And here's the way you can do that. Factor both the numerator.
Wait, you know what? I'll probably want to check that when you plug into. Gotta make sure this factors out. So at the top here would be x minus 2, x plus 2 over x minus 2, x plus 3. These cancel out. X plus 2, x plus 3. Then plug in the 2, 4 over 5. Alright, that's good. I'll keep this.
Numerator and denominator as much as you can. Right?
So
Or
that's the
plug in the, why don't you plug in the number? Plug in one of those numbers and see what you get. You can do it that way too. But if you factor as much as you can, what you're going to get is x plus 2, x minus 2, all over x plus 3, x minus 2. You with me on that one? Okay. Now, you need to get both all the discontinuities first before you start crossing stuff out. Are you ever going to be able to cross out a discontinuity and just eliminate the discontinuity? We learned that from domain, right? You can't ever just cross out a domain issue and then say, my domain's fine. No, you can't do that, right? You still have to write it down. So firstly, write down where your discontinuities are. So discontinuities x equals negative 3, and x equals 2. This will tell you which is which. That will tell you which is which. Which one can you cross out? The 2 or the negative 3? The 2. If you can cross it out, what does that tell you about the discontinuity at x equals 2? That's a hole. If you can cross it out, that means the function goes like this, and then it misses that one point and continues. So this thing, that's how you find it out. If you crossed out the discontinuity, you can't ever get rid of it. But if you're able to factor it out, that's a hole. Tell me something. You're completely factored, right? Can you cross out the x plus 3 at all? So what does it tell you about the discontinuity that occurs right there? That's an asymptote, and that's how you determine it. No, it's not hard. It's factoring and crossing stuff out. What you cross out is called a hole. What you don't cross out is called an asymptote. At least for rational functions, that's the way it works. I'm not going to give you another example because I think that's pretty straightforward. Is that pretty straightforward?
Yeah.
Awesome. Let's go ahead, let's prove something here real quick. Let's prove that the absolute value of x is continuous everywhere. Now, can you picture the absolute value of x in your head? Is it continuous everywhere?
Yep.
Do you ever pick your pencil up?
No.
Then it's continuous everywhere. That's what graphically it means. Let's figure out how to prove that. It's going to be similar to some of our one-side limits we've already worked with. Is absolute value of x continuous everywhere? And you go, let's see, looks like this. Yep, done. No, we can't do that. There's not
Should be able to do that.
That'd be awesome. Here's our proof with some limits, okay? What we want to prove for, God, that was pretty funny, I like that. Is that the limit exists at every point, that the limit equals the function value at every point, and that even at that weird place where it comes together, that exists. So here's how we're going to define it, all right? We're going to define absolute value of x in an interesting way. We're going to say that absolute value of x, you already know this one. It's x, and it's negative x. In fact, I think we can probably do that too. But this will make it even more interesting. For x is bigger than 0, for x is less than 0. Let's make it 0 for x equals 0. The reason why this looks funny to you and why I don't have an equality here is because, do you remember what we ran into with limits as far as checking the endpoints? You remember we ran into limit? There is no limit at an endpoint. You have to check the endpoints themselves, right? So we would run into this situation anyway. If I had an equal sign, that would dictate an actual endpoint. You follow me on that? So what I'm saying is that that's basically an open interval. We can check that with our knowledge of polynomials and continuity, no problem. Same thing with this one, that we'll have to check with one-sided limits. So here's what we know. Is this a polynomial?
Yeah.
Sure, it's the most simple polynomial. Well, besides a constant, that's like the most simple polynomial you can have, right? Just x. Are polynomials continuous everywhere?
Yeah.
Then this is continuous everywhere. It's a polynomial. What that means is continuous. Hey, is this a polynomial? Sure. That means it's continuous. Now, that is, well, technically a polynomial, right? That's just that one, but it's one single point. This is the point 0. So when you get 0, it gives you 0. That's where you come together on your absolute value. What we need to check is only this. we need to check that the one-sided limit of this one equals 0, and the one-sided limit of this one equals 0. That's what we can check. If we can prove that, then we know that that's continuous everywhere. The limit of this equals 0, the limit of this equals 0, the function is defined at 0, therefore all three pieces come together. Do you see what we're trying to do here? If you don't, then I need to know. Yes or no? Some people are just looking, yes or no? Okay. Sometimes I say I get deer in the headlights. Yes, I'm looking at you. Sometimes I wonder if I have a lazy eye, and it's like I'm looking and you're thinking, is he looking? I had a teacher with a lazy eye once. It was horrible, I probably shouldn't say this. It'd be like this, like looking at you, and then you're like, yeah, I get it. And then she would switch it. Yeah, that was pretty interesting. She had fun with it though. She really did. She had fun with it. Good lady. Okay. Or man, I'm not naming names. I just had a teacher once. Whatever. All right, so let's go ahead and do this. We're going to check this, the limit as x approaches 0 from the right. Look what we're doing. X is positive, right? So from the right for x. From the left for negative x. And we'll see what each of these things
Well, without the left and right, it's 0 anyway, right? So these are both 0, right? I think. Maybe?
are. So from the right-hand side, where does x go from the right-hand side as you approach 0? It goes to 0. It's a polynomial. You can plug it in. It's going to 0. Where does negative x go as you approach 0 from the left? Does it also go to 0? It goes to 0. That checks it right there. It says that the limit, the one-sided limit exists. This limit clearly exists as continuous. This limit exists. It says going to the point that is also defined. It says the limits exist. The point exists, and they all equal each other. That means that you're continuous everywhere, and that's how you prove it. The point that clearly exists is continuous. This limit exists. It says going to the point that is also defined. It says the limits exist. The point exists, and they all equal each other. That means that you're continuous everywhere, and that's how you prove it. Okay, we got to move on for a little bit. What right now we're going to talk about is something to do with compositions and how we can use compositions up very much to our benefit in functions. Now stick with me here. We're kind of proving stuff today if you haven't noticed. Let's say that there's a certain function that as x approaches some number, we'll call it c, the limit definitely exists, and we'll call it L. And let's also say there's another function f, and it's continuous at L. Well, then check this out. We're going to find out right now what happens when we compose g onto f, or f of g in other words. So what happens if we take a limit as x approaches c of f of g of x? A composition. You guys have seen compositions like that before, yeah? Well, this is kind of interesting, just check it out for a minute. Would you agree that if the limit exists, then the limit of g of x as x approaches c is equal to the limit, yes, but it's also equal to g of c, right? So then as we're plugging in c, this is g of c, but that's also equal to the limit. So that's the same thing as f of L.
Whoa, what's that jump?
Limit. So that's the same thing as f of L. The reason I had the extra limit in there, I don't need that. So if x approaches c, then g of x approaches L. You with me on that one? I had the extra limit, I didn't need it. If g of x approaches L and f is continuous at L, then we know if f is continuous, we can just plug that number in. This is going to be equal to f of L. Now the cool thing is we'll make a substitution right here. We'll say, all right, well then we can do f of, how much is L equal to? Not just g of x.
G of x is approaches c.
The limit of g of x. As x approaches c. What that proves to you is you can separate limits by composition. So this says, look at that. This is a composition of f of g of x. We can pull the f outside of the limit. We can take the limit of the g of x and then apply the function. That's really interesting, yeah. F has to be continuous to L because when you compose that, you're actually not plugging C into F. You're plugging L into F. Does that make sense? You're plugging C into G. The limit of G as x approaches C gives you L. You're taking that L, you plug it into F. Since F is continuous at L, you can make this jump. To say, if I plug in the C, that's going to go to L. If I plug in the L, right here, that's going to go to f of L because it's continuous. You with me on that one? Since that happens, we can make that jump and say, oh, but wait, L is equal to the limit of g of x as x approaches c. And that proves our composition for us. Say we can separate limits by composition. So this says right here, we can separate limits by composition. Let me give you a quick example of how we can do this, how we can use it. Talk about maybe one more thing that we've done for today. So, quick example. Let's say we have a limit as x approaches 4 of the absolute value 10 minus 3x squared. Here's basically what this says we can do. Do you understand how this really is a composition of one function and the absolute value function? Do you guys see that? What it says is that you can treat this, because we haven't really defined limits of absolute value. We haven't really talked about that. We've had to do one-sided limits for things like this so far. So if we haven't really talked about it, there's something that we actually can do here. This says, well, wait, if that's a composition, then this means, since we've proved absolute value of x this is why we had to do it, why you're like, why didn't we use it here? We've already proved absolute value of x is continuous everywhere. You with me? And for this function to work, for this composition to work, f had to be continuous at a point. Well, it's continuous at all points, therefore we can do the composition. Did you see the difference there? We couldn't use it here because that would be circular, but we had to prove it once. We proved it, now we can use it for absolute value. Say, oh, well, well, wait, that's a composition of the function that's continuous everywhere. I can pull that outside. If you remember, can separate limits by composition. So this says right here, we can separate limits by composition. Let me give you a quick example of how we can do this, how we can use it. Pose g onto f, or f of g in other words. So what happens if we take a limit as x approaches c of f of g of x? A composition. You guys have seen compositions like that before, yeah? Well, this is kind of interesting. Just check it out for a minute. Would you agree that if the limit exists, then the limit of g of x as x approaches c is equal to the limit, yes, but it's also equal to g of c, right? So then as we're plugging in c, this is g of c, but that's also equal to the limit. So that's the same thing as f of L. Reason I had the extra limit in there, I don't need that. So if x approaches c, then g of x approaches L. You with me on that one? I had the extra limit, I didn't need it. If g of x approaches L and f is continuous at L, then we know if f is continuous, we can just push L. On that one, I had the extra limit, I didn't need it. If g of x approaches L and f is continuous at L, then we know if f is continuous, we can just put that number in. This is going to be equal to f of L. Now the cool thing is we'll make a substitution right here. And we'll say, all right, well then we can do f of, how much is L equal to? Not just g of x.
G of x is equal to c.
The limit of g of x. As x approaches c. What that proves to you is you can separate limits by composition. So this says, look at that. This is a composition of f of g of x. We can pull the f outside of the limit. We can take the limit of the g of x and then apply the function. That's really interesting, yeah. F has to be continuous at L because when you compose that, you're actually not plugging c into f. You're plugging L into f.
So basically, with the limit of g of x, you're getting like the point y, alright? And you're basically just plugging that point into the other function.
Does that make sense? You're plugging c into g. The limit of g as x approaches c gives you L. You're taking that L, you're plugging into f. Since f is continuous at L, you can make this jump. To say, if I plug in the c, that's going to go to L. If I plug in the L...
Yeah, then that would be the same as f of g of x.
Right here, that's going to go to f of L because it's continuous. You with me on that one? Since that happens, we can make that jump and say, oh, but wait, L is equal to the limit of g of x as x approaches c. And that proves our composition for us. Say we can separate limits by composition. As x happens, that's going to go to f of L because it's continuous. You with me on that one? Since to say, if I plug in the c, that's going to go to L. If I plug in the L, right here, that's going to go to f of L because it's continuous. You with me on that one? Since that happens, we can make that jump and say, oh, but wait, L is equal to the limit of g of x as x approaches c. And that proves our composition for us. Say we can separate limits by composition. So this says right here, we can separate limits by composition. Let me give you a quick example of how we can do this, how we can use it. Talk about maybe one more thing that we've got for today. So, quick example. Let's say we have a limit as x approaches 4 of the absolute value 10 minus 3x squared. Here's basically what this says we can do. Do you understand how this really is a composition of one function and the absolute value function? Do you guys see that? What it says is that you can treat this, because we haven't really defined limits of absolute value. We haven't really talked about that. We've had to do one-sided limits for things like this so far. So if we haven't really talked about it, there's something that we actually can do here. This says, well, wait, if that's a composition, then this means, since we've proved absolute value of x, this is why we had to do it, why you're like, why didn't we use it here? We've already proved absolute value of x is continuous everywhere. You with me? And for this function to work, for this composition to work, f had to be continuous at a point. Well, we've proved, well, wait, if that's a composition, then this means, since we've proved absolute value of x this is why we had to do it, why you're like, why didn't we use it here? We've already proved absolute value of x is continuous everywhere. You with me? And for this function to work, for this composition to work, f had to be continuous at a point. Well, it's continuous at all points, therefore we can do the composition. Do you see the difference there? We couldn't use it here because that would be circular, but we had to prove it once. And for this function to work, for this composition to work, f had to be continuous at a point. Well, it's continuous at all points, therefore we can do the composition. Do you see the difference there? We couldn't use it here because that would be circular, but we had to prove it once. We proved it, now we can use it for absolute value. So, therefore we can do the composition. Do you see the difference there? We couldn't use it here because that would be circular, but we had to do the composition. About that. We've had to do one-sided limits for things like this so far. So if we haven't really talked about it, of one function and the absolute value function. Do you guys see that? What it says is that you can treat this, because we haven't really defined limits of absolute value. We haven't really talked about that. We've had to do one-sided limits for things like this so far. So if we haven't really talked about it, there's something that we this. So number 1 is satisfied, and number 2 is satisfied. Would you agree with that?
The limit does not exist if f of g approaches infinity, although you can see it that way. That's because infinity is not defined as a real number. Really. Anyway, you write that the limit equals infinity, although you should be aware that it's not a limit value. Huh. I was wondering that too. That didn't really make sense.
couple problems. Once we proved it as x approaches 4 of the absolute value 10 minus 3x squared. Here's basically what this says we can do. Do you understand how this really is a composition of one function and the absolute value function? Do you guys see that? What it says is that you can treat this because we don't.
So is he saying that since we already proved the absolute value function and the function inside is a polynomial, that you can separate them since we already proved both are continuous? How do I mean it?
Value. We haven't really talked about that. We've had to do one-sided limits for things like this so far. So if we haven't really talked about it, there's something that we actually can do here. This says, well, wait, if that's a composition, then this means, since we've proved absolute value of x is, this is why we had to do it, why you're like, why didn't we use it here? We've already proved absolute value of x is continuous everywhere. You with me? And for this function to work, for this composition to work, f had to be continuous at a point. Well, it's continuous at all points, therefore we can do the composition. Do you see the difference there? We couldn't use it here because that would be circular, but we had to prove it once. We proved it, now we can use it for absolute value. Say, oh, well wait, that's a composition of a function that's continuous everywhere. I can pull that outside. If you remember, I hope you do. You remember? Well, I actually did that with cosine before. Remember me doing that with cosine? The reason why we could do it is because cosine is continuous everywhere. And now I've proved it for compositions. We used it earlier, but I've proved it now that we can, in fact, do that. So we say take the limit of this and then take the absolute value, and that will work just fine for you. You can separate limits by composition. What's the limit of 10 minus 3x squared as we approach 4? Separate limits by
Still not getting this
about that. We've had to do one-sided limits for things like this so far. So if we haven't really talked about it, there's something that we actually can do here. This says, well, wait, if that's a composition, then this means since we've proved absolute value of x is, this is why we had to do it, why you're like, why didn't we use it here? We've already proved absolute value of x is continuous everywhere. You with me? And for this function to work, for this composition to work, f had to be continuous at a point. Well, it's continuous at all points, therefore we can do the composition. Do you see the difference there? We couldn't use it here because that would be circular, but we had to prove it once. We proved it, now we can use it for absolute value. Say, oh, well wait, that's a composition. Of the function that's continuous everywhere, I can pull that outside. If you remember, I hope you do. You remember? You remember? You remember? Well, I actually did that with cosine before. Remember me doing that with cosine? The reason why we can do it is because cosine's continuous everywhere. And now I've proved it for compositions. We used it earlier, but I've proved it now that we can, in fact, do that. So we say take the limit of this and then take the absolute value, and that will work just fine for you. You can separate limits by composition. What's the limit of 10 minus 3x squared as we approach 4? Don't all speak at once.
38.
Negative 38?
No, 38.
38. Wait, inside.
Oh, negative 38.
So this says you'll have the absolute value of negative 38 because the limit of 10 minus 3x squared is polynomial. You plug in the number, you get negative 38. Then we take the absolute value of negative 38, we get, and that's our answer. So the limit would be 38. Couple notes before we go. If two functions are continuous everywhere, their composition will be continuous everywhere. Absolute value with anything inside, it can be considered a composition. Two functions are continuous everywhere, their composition is continuous everywhere. It's for this reason. If this always works, if this is always continuous and that's always continuous, and you can compose them any way you want, it's still going to be continuous.
Go.
One last thing about inverses. We haven't spoken about them yet. We will just briefly. If f is continuous on its domain, then f inverse will be continuous on its domain. But remember that with inverses, the domain of an inverse is the range of your original function. So,
Okay.
if f is continuous on its domain,
The inverse will have a continuous range.
f inverse, the inverse of f, will also be continuous on its respective domain
Wait, not its range?
But keep in mind that the domain of f inverse is the range of your original function. You switch
Okay.
x and y, right? So
All
the
right.
range becomes domain, domain becomes range. So if f is continuous on its domain, f inverse will also be continuous on its respective domain, but that is the range of your original function, the range of f. Okay, in the last minute that we have, let me give you one quick example. Let's just say f of x is x cubed. Is x cubed a polynomial? That means it's continuous everywhere. So it's continuous on the entire domain, entire real number
What
system.
exactly is a polynomial? I know what they look like, but... Constants, variables, exponents. Go.
So it's a polynomial. It's continuous on negative infinity to infinity. Its range. What's its range? What's its range? Oh, not just that.
Yeah, its range would be the same.
It also goes from negative infinity to infinity. Yeah, all real numbers. So if we found the inverse, do you remember how to find the inverse?
Swap the x and y and then solve for y, I think. So... like that.
Yeah, you make y equals x cubed, you switch your variables, x equals y cubed, you solve for your y, the cube root of x equals y, and therefore f inverse of x equals the cube root of x. Here's what's cube root. Here's what I know about this already. I know that for a fact, because this is the inverse of this polynomial, I don't have to do any more work with it. I guarantee you that that's continuous on the range of my original function. So because the range of my function was negative infinity to infinity, not the domain, not really concerned about that. That's a polynomial, it's continuous everywhere. But my range was negative infinity to infinity. What this says is that this must be continuous from negative infinity to infinity, continuous everywhere. If the range is everything, the inverse function has a domain of everything. So it's continuous because of the range, negative infinity to infinity.
Why is it making a bookmark? Is bookmark control D? Oh, that's why. Okay. Function is continuous both for f of x equals x to the power of 3 and its inverse between negative and positive infinity. But it is not the case for f of x equals x squared. Okay, why did he say that? I don't think he ever said that x squared was continuous. Here's my question. Okay. How's the domain of the cube root of x equal to negative infinity, positive infinity? I was wondering, because I don't think the domain can be a negative infinity, positive infinity. Shouldn't it be equal to 0, positive infinity instead? The range would be all real numbers, so I'm pretty sure. Maybe. Or maybe it can only be... No, it can be negative range, I think. Wait, because root 3 of negative numbers are real. Oh, okay. Oh, okay. Wait. How do I put something in front of the square root? Cubed root of negative 8. Because if you did negative 2 times negative 2 times negative 2, that works. But if you do that in a square root, you're always going to get a positive. Because it's 2. Okay. Alright. Makes sense.
Well, good afternoon, welcome back. We're going to continue talking just a little bit about some limits. One application of these, and continuity. One application of continuity we're going to talk about today is something called the intermediate value theorem. Now, here's the idea. Let's say that I gave you some continuous function. So it's definitely a function. F of x, and I say this function is defined between a and b, or let's just put some endpoints on it, a to b. Can you tell me how high is this point?
Yeah, y.
That would be certainly y, but let's not make it in terms of y. Let's make it in terms of f.
Oh, f of a.
How high would that
F of a.
point be? F of a is a good start. Well, that'd be how high it would be. So if this is a, how you figure the height out is you plug that into your function, right? Or in other words, f of a. Cool. How high is this point?
of B.
All right, now let's follow the pattern there. So f of A, f of B, very good. Gives us our heights. Now here's the question. Firstly, let me say that f is certainly continuous. Do you see that f is continuous on the interval AB?
Yep.
So f of x is continuous. In fact, since it has those endpoints, we could say it's continuous on the closed interval as well.
Go.
Here's my question. Let's suppose that I picked some random point, some arbitrary point between f of A, some arbitrary value between f of A and f of B. Maybe like here, and I'll call it K.
Okay.
So let's say that K is between f of A and f of B. Here's my question. If I find the input that gives me this output, if I can find the input that gives me that output, will it be between A and B? That's the question.
Yeah.
If f is continuous, here's what it says. It says if you give me any point, any value between f of A and f of B, something in here, I can guarantee you that the input that would give me that value lies between A and B.
Yeah, it'd have to be.
And here's how we say this is the intermediate value theorem. It says for any value k, there's at least one point, at least one value between A and B that will give you that, the function of that value gives you k. So in other words, if k is between f of A and f of B, then there's at least one x value at least. There could be more. If you don't have a one-to-one function, you could have several. There's at least one number let me call it C, okay? At least one number,
Gives
we'll
you
call
K.
it C. Such that f of C will give you K.
Okay, pretty easy.
Oh, you know what? I need to add one little part of here. There's at least one number C where C is between, that's kind of a key point, where C is between A and B. And f of C equals K. You want to hear it in plain English because that's kind of mathy, right? It says, well, say K is between f of A and f of B, then there's at least one number, C, where C is between A and B, and f of C equals K. Now that makes perfect sense to me, but here's what it says in English for you if you're like, oh yeah, I don't understand.
So he's saying that the y point, which is k, has to come from an x point that's between A and B.
Understand this. Here's what it says. If you give me any, if your function's continuous, that means there's no holes, there's no asymptotes, there's no jumps. You get me? It's a smooth curve. If you give me an output between these numbers, my input will be between these numbers. So here's my input and my output, right? For those respective values. Here's my input and my output. It says you give me an output anywhere in this range, the input must be somewhere between this range. And there's going to be at least one such that this input gives you that output. Could you pick a different point? Sure. You can pick any one of these points, but no matter what, that output is going to be mapped to at least one input. At least one. Now, if you did a curve like this where you had that, you could have more than one, right? 1, 2, 3, however many you wanted. You could definitely do that. If it's continuous, you'll have at least one, though. How many people understand the idea of that? And that's called the intermediate value theorem. Do you want to see kind of a cool application for this?
Yeah.
I'm excited about it. Hope you're excited about it. Do you want to see?
Yeah.
Ah, good. Here's a cool application. You can actually approximate roots. You know what roots are, right? Where functions cross the x-axis. You can approximate that with this idea. Here's the plan. Let's say that I have this certain function. It looks like that, though. Well, of course, this height is f of b. And that height's f of a. Here's the idea using the intermediate value theorem. You know for a fact that this was true, right? If I give you some specific value here, you can find me an input in this range such that that gives me that output. Are you with me on that? You can give me any specific output that you want to, and I can find you the input that's in this range. You understand that? Here's what it says for this. It says, let's suppose that you know that f of a is positive and f of b is negative. So in other words, the signs are different. If the signs are different, then what you know for sure is that it crosses the x-axis, right? In other words, it says that if I say, find me the point of 0, that's an intermediate value right there, right? It's between those values. If I say, find me the input that gives me 0, we need to, or we know for sure that that actually exists. If our signs are different, then of course we cross the x-axis, right? And according to the intermediate value theorem, it says, well, you're continuous, right? Your signs are different. So if we're going from positive to negative according to our interval of outputs, then 0's got to be between those because we went from positive to negative. So I can say with certainty, according to the intermediate value theorem, that there. So I find you the input that's in you do some specific value here. You can find me an input in this range such that that gives me that output. Are you with me on that? You can give me any specific output that you want to, and I can find you the input that's in this range. You understand that? Here's what it says for this. It says, let's suppose that you know that f of a is positive and f of b is negative. So in other words, the signs are different. If the signs are different, then what you know for sure is that it crosses the x-axis, right? In other words, it says that if I say, find me the point of 0, that's an intermediate value right there, right? It's between those values. If I say, find me the input that gives me 0, we need to, or we know for sure that that actually exists. If our signs are different, then of course we cross the x-axis, right? And according to the intermediate value theorem, it says, well, you're continuous, right? Your signs are different. So if we're going from positive to negative according to our interval of outputs, then 0's got to be between those because we went from positive to negative.
Sure.
So I can say with certainty, according to the intermediate value theorem, that there is going to be an input such that f of that input will give me an output of 0. Let me write some of that out for you so that you have that. It says that if your signs are different, f of a and f of b have different signs. you ever thought about two things having different signs, then you know 0 will be between those two numbers, true? Let's say negative anything and positive anything, you know that 0 is between them, yes? If 0 is between them, that means you can apply the intermediate value theorem. If 0 is between them, then you must have a certain input that will give you 0. That's applied, using the intermediate value theorem applied to this case. So, it says if the signs are different, there must be at least one root on that closed interval. That's all it says, and that's all that says. It's just a very specific case where your signs are different, you know 0 is between them. You can say for any output, you can give me a specific input on that domain, on that interval. Would you like to see it in application, how you would actually do this? Now, of course, we have calculators, right? You just go, oh, let me use my 0 button for my graphing, and it will do it very, very fast. But let's say that all calculators broke. Isn't that an interesting idea? What if they all broke, which they're not going to? What if they did? You could now do it. Here's the example. I'll give you this function. I'll just explain very quickly the idea. You'd find some point on this graph. I know for sure that I don't really know exactly how this graph looks, but I know for sure it's continuous everywhere. Can you explain to me why this is continuous everywhere? Very good. So this is definitely going to be continuous on any closed interval. So I know this graph looks something like that, all right? I know for sure. And it goes forever. Well, here's the deal. I'd plug in some numbers at some point, and what I would find is that when I plugged in 1 and when I plugged in 2, they had different signs. For instance, f of 2 was up here, f of 1 was down here. That means that somewhere between 1 and 2, according to the intermediate value theorem as used for approximating roots, I know that I'm going to have some number that gives me a 0 there. Does that make sense to you?
Yep.
I know it's going to be within that range because, well, my signs are different. So here's how you go about doing that. You'd make yourself up a table, X, Y, and what you'd do is you'd have every value between 1 and 2 according to like a tenth or something. So like 1.1, 1.0, and 1.1, 1.2, 1.3, 1.4, and so on. And this is very time consuming, okay? You're not going to do this all the time. You can use your calculator, of course, but this is how you would do it. I'm just giving you the how. Am I expecting you to do this all the time? No, heck no. But this is how it would work according to our theorem over here. What you do is you take all these numbers and you would plug them into that function. You're going to get a negative, a negative, a negative, but somewhere it's going to change to a positive. Are you with me? It's saying like, here it's negative, but somewhere over here it's going to change to a positive. And I think if I've done this right, it's between 1.3 and 1.4. So this would be negative, 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 positive, positive, positive. Right here, well, you just narrowed the range. Right now you know that the root has to be between 1.3 and 1.4. Do you see how we've used the same idea, we just made it smaller? So you take that and you go, okay, let's try this again. X, Y, and you'd start now with 1.30, 1.31, 1.32, and you'd continue that. And then you'd find out which one of those is negative and where the breakoff is to where it becomes positive. Do you see how you can get very accurate with this? You can get to however many decimal places you want. Already I know it's going to be 1.3 something, and then I would do this one. I find out it's 1.3 something. I could find out all those numbers as much as I want, as accurate as I want to be. And that's one way you could actually set up a computer program to do that for you. Program a calculator that would do that for you. It might take a little bit of time, but it's possible. How many people understood the idea of applying that? All right, good deal. So just a little kind of nice something we can use there. Now, are you ready to learn how we can take limits and use them? First, I've already kind of shown you a basic idea of how to do this, how to find.
Okay, so he's bringing it back to the first video I see. Okay, so what I'll do is I'll go back to puzzle and math notes. Okay, and then I'll do Limits of Infinity Part 1, Part 2, Continuity. Then I'll watch this video, and then do Definition of the Limit. And then I'll move on to derivatives, which I have no idea what they are. So that's kind of cool. How many videos does he have on derivatives? A lot. What's the hardest, I wonder? Limits and continuity, really? Most other things are just calculation. Hardest concept in Algebra 2, I wonder. I never did trig functions in Algebra 2. That's linear algebra. Okay, anyway. So for these, right? Would I be able to just set these equal to 0 and then plug in a 1 and a negative 1? Or wait, plug in whatever would make it positive and whatever would make it negative. We'll see. Maybe I'll just read it, honestly. In the previous section we saw limits that were infinity, and now it's time to take a look at limits at infinity. By limits at infinity we mean one of the following two limits. In other words, we're going to be looking at what happens to a function if we let x get very large in either the positive or negative sense. Also, we'll soon see these limits may also have infinity as a value. First, let's note that the set of facts from the infinite limit section also hold if we replace the limit of limit as x approaches c with the limit of as x approaches infinity, or the limit as x approaches negative infinity. The proof of this is nearly identical to the proof of the original set of facts, with only minor modifications to handle the change in the limit, and so is left to you. We won't need these facts much over the next couple of sections, but they will be required on occasion. In fact, many of the limits that we're going to be looking at will need the following two facts. If R is a positive rational number and C is any real number, then it's equal to 0. If R is a positive rational number, C is any real number, and x of R is defined as x is less than 0, then okay. The first part of this fact that should make sense if you think about it, because we are requiring R is greater than 0. You will know that x to the power of R will stay in the denominator. As we increase x, then x to the power of R will also increase. So we have a constant divided by an increasingly large number, and so the result will be increasingly small, or it's going to 0. Okay. Second part is nearly identical, except we need to worry about x of R being defined for negative x. This condition is here to avoid cases such as r equals half. If this r were allowed, we'd be taking the square root of negative numbers, which would result in a complex. We want to avoid that. Note as well that the sign of c will not affect this answer. Regardless of the sign of c, we'll still have a constant divided by a very large number, which will result in a very small number. The larger x get the smaller. The larger x gets, the smaller the fraction gets. The sign of c will affect which direction the fraction approaches 0, the positive or the negative, but it still approaches 0. If you think about it, this is really a special case of the last fact from the facts in the previous section. However, to see a direct proof of this fact, we see the proof of various limit properties in the section in the extra chapters. Let's start off with examples, with one that will lead us into a nice idea we use on a regular basis about limits at infinity for polynomials. Okay. I'm actually not sure how to do these. Our first thought here is probably just to plug infinity into the polynomial and evaluate each term to determine the value of the limit. It is pretty simple to see that each term will do in the limit. So this seems like an obvious step, especially since we've been doing that in other limits in the previous sections. So let's see what happens if we do that. As x approaches infinity, the x to a power can only get larger, and the coefficient on each term, the first and third, will only make the term even larger. And so we look at each term. So if we look at what each term is doing in the limit, we get the following. So infinity, negative infinity, and negative infinity. Now we've got a small but easily fixed problem to deal with. We are probably tempted to say that the answer is 0, because we have an infinity minus an infinity, or maybe negative infinity, because we're subtracting 2 infinities off of 1 infinity. However, in both cases we'd be wrong. This is one of those intermediate forms that we first started seeing in the previous section. Infinities just don't always behave as real numbers do when it comes to arithmetic. Without more work, there is simply no way to know what infinity minus infinity will be. So we really need to be careful with this kind of problem. To read a little more about this, see the types of infinity section in the extras chapter. So we need a way to get around this problem. What we'll do here is factor the largest power out of x out of the whole polynomial as follows. Why? If you're not sure you agree with the factoring above, there's a chance you haven't really been asked to do this kind of factoring prior to this. Then recall that to check, all you need to do is multiply the x to the power 4 back through the parentheses to verify it was done correctly. Also, an easy way to remember how to do this kind of factoring is to note that the second term is just a original polynomial divided by x to the power 4. This will always work when factoring a power of x out of a polynomial. Seriously? Couldn't you just factor out an x? Instead of x to the power 4? I don't get it. the first limit is clearly infinity, and for the second limit, we'll use the fact above on the last two terms. Therefore, using fact 2 from the previous section, we can see that the limit will be Okay, so we took the largest power out, so that it would overpower the smaller ones, right? So when you plug in infinity, this whole thing is like irrelevant. So for this one, third t to the power of 5 plus 2t cubed minus t squared plus 8. Well, wait, there's an 8 now. Oh wait, that doesn't matter. Well, wait, now there's the same power on the inside. So I actually don't know. Remember that all you need to do to get the factoring correct is divide the original polynomial by the power of t that we're factoring out. Now all we need to do is take the limit of the two terms. In the first, don't forget that since we're going out towards negative infinity, that we're raising t to the 5th power, that the limit will be negative. What? I gotta look up a video for this, dude. Like, what is going on?
Infinity for a given polynomial. So in part A we have limit 7x to the 5 minus x to the 7 plus 200 when x goes to positive infinity. So you have to use this rule. Limit x to the n when n goes to infinity equal to positive infinity. But here you have to take the highest power only and no need for the other terms when x goes to infinity or negative infinity when we are dealing with polynomials inside limit. So you have to take the highest power term, and this is the highest power term, which is negative x to the power 7. So this limit equals to limit negative x to the 7 when x goes to positive infinity, and this is equals to negative positive infinity to the power 7, and positive infinity to the power 7 equals to infinity, and we have negative sign outside, so it will be a negative infinity.
Huh?
Limit equals to limit negative
What? Okay, highest power.
x to the 7 when x goes to positive infinity, and this is equals to negative positive
Okay.
infinity to the power 7.
Is it really that simple then? So do you even have to factor it out? You could just say you just look at this. Say a third of positive infinity to the power of 5. Or this would be negative. Yeah, like what's the point of factoring out? I don't get it.
And positive infinity to the power 7 equals to infinity, and we have negative sign outside, so it will be a negative infinity.
So if it seems like if the highest power, if the variable with the highest power is negative, then you just use the negative sign on the positive or negative infinity, whatever you plug in, and then that's your answer, or what? So like B would be positive infinity, C would be negative infinity, and D would be but it has 2. Wait. D would be positive infinity.
Now for the
Seems
second
easy.
one in part B, this is our limit negative 5x to the power 8 plus 56x minus 31 when x goes to negative infinity. So you have to take the term with the highest power and cut the other terms. So we have this term as the highest term. So we have limit
Oh, positive infinity and is even, negative infinity and is odd. Wait, what?
negative
Okay, I actually don't get that.
5x
What?
to the 8
What's this about?
when x goes to negative infinity. And this is equals to negative 5 multiplied by negative infinity to the 8. And 8 is an even exponent, so you have to cancel the negative sign here. And
Oh,
the
okay,
answer will
okay.
be negative 5 multiplied by positive infinity equals to negative infinity.
Okay, so you gotta remember that the sign, it's gonna be positive if it's even. And that's only for negative infinity. You have to worry about that. I think I get it now. So if I go to the practice problems for this, f of x equals 4x power of 7 minus 18x cubed plus 9. Negative infinity. You only care about the 4x power of 7. 4, negative infinity, power 7. It's an odd, so the negative stays. Negative infinity. Limit of f of x as x approaches negative infinity is negative infinity. 4x. I wonder why the videos I was watching didn't go over this. Or maybe I missed it. 4 infinity power 7. It's a positive. It's gonna stay positive. Positive infinity. The limit of f of x as x approaches infinity equals positive infinity. Okay. So for 2, well, can I do this in my head? I'm gonna get rid of that cube root. Or can I? What did they do? I don't get this property stuff they're doing. Then use basic limit properties along with fact 1 to evaluate.
And denominator, a fraction, if you will. So just remember this is in the form of a numerator over a denominator. So for something that looks like this, a rational expression in your limit as x approaches infinity or negative infinity, there is a really fast way of getting the limit, and it's a shortcut. It's really the fastest way, and I'm going to show that to you first. Basically, all you do is compare the degree of the numerator and the degree of the denominator, the degree of the polynomial on top and the degree of the polynomial on the bottom, to find what the limit should be. And there are 3 cases I want to show you. I will show you the formal algebraic official way of finding the limit of a rational expression for x approaching infinity. But first, I think it's really useful to see this fast way based on these 3 cases. So with a shortcut for a rational expression, compare the degrees of the numerator and the denominator. The degree is the highest power that appears in a polynomial, so the degree of the numerator is the highest power of x that appears in the top, and the degree of the denominator is the highest power of x that appears in the bottom.
In this lesson, we'll take a look at two limits at infinity involving a polynomial function. Determining limits at infinity of a polynomial function is the same as determining the end behavior or long-run behavior of a polynomial function. First, we have the limit as x approaches positive infinity of negative 4x cubed plus 5x squared. So what we're trying to do here is determine what's happening to the function value as x increases in the positive direction without bound. And there are a couple ways of doing this. Notice how the first term has degree 3 and the second term has degree 2. So as x increases without bound, because this first term has a higher degree, it's going to outweigh the terms of lower degree. Therefore, we can determine this limit by just considering the term with the highest degree, or in this case, the term negative 4x cubed. As x increases without bound, x to the third is going to be a very, very large positive number. But then we have to multiply that very large positive number times negative 4, making it a very large negative number. Therefore, this limit is equal to negative infinity, which we know does not exist. If this argument isn't convincing enough, another method is to factor out the highest power of x in the polynomial function. So in this case, we would factor out x cubed from each term in the polynomial. So let's go ahead and do that. We'd have the limit as x approaches positive infinity, and then we're going to factor out x to the third. That's going to leave us with negative 4 plus, now this is a little tricky. If we factor out 3 factors of x from 5x squared, this will leave us with 5 divided by x. Notice if we multiply x to the third times 5 divided by x, one factor of x would simplify out, leaving us with 5x squared. And now because we have a product here, we can write this as a product of two limits. We'd have the limit
Oh, that's what he was doing. He's just rewriting
as
it as a
x
product of two limits.
approaches infinity of x to the third times the limit.
I was so confused because like the videos, he like never uses limit properties.
As x approaches infinity
But in the notes,
of negative 4 plus
I guess they just kept using them.
5 divided by x. And now in this form, it should be easier to see that the limit as x approaches infinity of x cubed would approach positive infinity. But for the second limit, notice that negative 4 is not affected by x as it approaches infinity, but 5 divided by x would approach 0. So the second limit would be equal to negative 4. Therefore, a very large positive number times a negative number does confirm our limit would be negative infinity. We'll verify this graphically after we take a look at our second limit. Now we have the limit as x approaches negative infinity of the same polynomial function, negative 4x cubed plus 5x squared. Again, we are able to determine this limit just by considering the term with the highest degree, which again is this first term. As x approaches negative infinity, we're now cubing a very large negative number, and since it's being raised,
I see it now. You just factor it out. Takes the limit of t squared. T squared is x as t approaches negative infinity. That would be positive infinity. For the ones on the right, t is in the denominator. So you plug in negative infinity, it's just going to go towards 0. So you don't care about those. Negative 2 is all that really is left. So you're left with negative infinity. Okay. The other way is definitely easier. Um, Okay. I don't even know what he did on these ones, because I just used the sign analysis. Start off by acknowledging that for x, as x approaches 3 from the left, x is less than 3. Okay. For the numerator, we can see that in the limit, it will just be 9. The denominator takes a little more work. You have x minus 3 approaches 0.
Of two limits, we'd have the limit as x approaches infinity of x to the third times the limit as x approaches infinity of -4 plus. And therefore the function values are approaching.
What's the pink thing you drew there?
This is the very famous limit. Check this out. What we'll do is put the x down. So we are looking at this as the limit as x approaching infinity of sine of 1 over x over 1 over x like this. And to do this, we can actually do a substitution, but not for integration, for limits though. So we'll take theta to be 1 over x. And notice when x is approaching infinity, this means theta will approach 0. So you see that this becomes the limit as theta approaching 0. And then on the top, we have sine of theta, and on the bottom we just have the theta here. And have a look right here, if you put a 0 in here, look, and this right here, and have a look, this is the very famous limit. Check this out.
Alright, let me try one of these, like 6. If x equals x cubed minus 2x plus 11, 3 minus 6x power of 5. And we're trying to find negative infinity, positive infinity. You do the same thing, but so factor out one of these. Positive infinity? Zero. Will you factor out the exponent from what? Oh, okay. Okay, man. So this is 0. I'm guessing that it's gonna be the same thing. So this is gonna be an asymptote. Okay. Alright, so what should I do here then? What the problems look like for this? I don't really know what to do because the videos and the assignments aren't really matching up well at all. I'm wondering, do I move on? Or... Alright, I think tomorrow I'm gonna read 2.7 to 2.9 and then watch 1.5. Okay. Because 2.7, 2.8 are in the video. Do I go back and read 2.6, I'm wondering? Alright, I'm not gonna go back and read 2.6. 2.7, 2.8, 2.9. Then do the video. Okay. Alright, that's it then.